Welcome to AI Podcast. Today we're digging into a new EMNLP paper called WebInject, led by Xilong Wang and Zhenqiang Gong at Duke University. It's about a stealthy way to hijack web agents.
Web agents, meaning those AI systems that browse websites for you, click buttons, fill forms, that kind of thing?
Exactly. Most of them look at screenshots of a page, reason over the pixels, and then decide where to click or what to type. WebInject shows how an attacker can nudge those pixels just enough to make the agent follow the attacker's command.
Nudge how? Are we talking about giant pop-ups screaming click here or something more subtle?
Much more subtle. Think of it like putting a nearly invisible film over the screen, a faint tint you and I wouldn't notice, but that gently steers the agent's perception. The trick is that the perturbation is implemented in the web page's own code, so when the browser renders the page and the agent grabs a screenshot, those tiny changes are baked in.
So the attacker only needs to control the web page content, not the user's computer or the agent itself. That sounds worryingly practical.
Right, that's the point. Prior work either injected very visible elements like decoy banners or assumed the attacker could directly alter the user's screenshot, which is unrealistic. WebInject aims for both realistic and stealthy. Modify page pixels through HTML or Canvas code so they survive rendering, scaling, and the screenshot step.
Okay, but how do you figure out which pixels to tweak? That pipeline from the page to the screenshot isn't simple. There's color management, resizing, all the browser magic. You can't just run gradients through the browser.
Exactly the core challenge. The mapping from the page's raw pixels to the final screenshot is not differentiable, so they train a small neural network surrogate that approximates that mapping. Then they optimize the perturbation against the surrogate using projected gradient descent, which is a standard way to keep changes small while pushing the output toward a target.
I'm with you. So they basically build a stand-in for the rendering process, learn how page pixels become screenshot pixels, and then use that stand-in to craft the tiniest possible change that makes the agent take some action. What counts as a target action here?
Things like clicking a specific button or coordinate. Imagine the legitimate task is pay your utility bill, but the attacker wants the agent to hit change payment method and paste a routing number somewhere else. WebInject's perturbation biases the agent toward the attacker's chosen click.
It sounds a bit like tricking a self-driving car with barely noticeable stickers on a stop sign. Humans still see stop, but the model gets confused.
Great analogy. To a person, the page looks normal. The agent, which relies heavily on pixel-level cues, gets a subtle visual nudge that changes its decision.
What about the research setup? How did they test this without building a fragile demo that only works once?
They evaluated on multiple sets of web pages, including real sites and synthetic pages, and across several popular vision language backbones that power these agents. The idea was to see whether the attack generalizes across page layouts and different agent models.
And the takeaway?
The attack was consistently effective and beat baseline methods. The authors argue that classic HTML prompt injections are either too obvious or too brittle, while screenshot-only adversarial patches don't fit the real threat model. By optimizing right where the agent actually sees the screenshot via a learned surrogate, WebInject maintains stealth and reliability.
Got it. I'm curious about the nuts and bolts for a second. When you say projected gradient descent, what are they constraining? Is it like a small norm bound so the page doesn't visually change?
Exactly. They keep the perturbation tiny so it remains imperceptible to users. And they pay attention to resizing too, because agents often rescale screenshots before feeding them into a model. During optimization, they make that resizing step differentiable so the crafted perturbation survives the rescale.
That's clever, but let me push on practicality. Do attackers need to know which model the agent uses?
In the paper, they work with open models and use them directly, so they do assume some knowledge. Transferability to closed models is an open question. A pragmatic attacker could try a small ensemble during optimization, but that's future work.
Right, and on the defender side, what can you do? If the pixels are essentially clean to the human eye, how do you catch this?
A few directions. One is DOM to visual consistency checks. If the page's visible pixels don't match what the DOM claims, like an invisible canvas layer writing tiny changes under legitimate elements, that's suspicious. Another is agent-side guardrails. Don't perform high-risk actions unless there's strong, redundant evidence. And browsers could explore sanitizing screenshots, for example, by randomizing rendering details or constraining color mappings to make gradient-based attacks harder.
So add friction where the attacker expects smooth gradients. Make the path from page to screenshot less predictable.
Exactly. Also, provenance signals. If the page is executing unusual canvas writes in regions the user isn't interacting with, flag it. You could even prompt the user for confirmation when the agent is about to take a sensitive step that was triggered by faint visual cues.
Let's circle back to limitations. What's the fine print the authors acknowledge?
First, the threat model. The attacker must control the web page content. That's realistic for compromised or malicious sites, but not every site. Second, the learned surrogate approximates one rendering pipeline. Hardware, OS, and browser differences could reduce reliability. Third, they didn't claim broad transfer to proprietary models. And finally, highly dynamic or authenticated pages might introduce layout churn that undermines a carefully crafted perturbation.
Right, so it's powerful but not magic. I'm also thinking about evaluation. Did they only show cherry-picked examples?
No, they tested across multiple datasets and models to show breadth. The abstract emphasizes extensive evaluation and significant gains over baselines. They avoid long, one-off anecdotes and focus on consistency.
Okay, now the so what. If I'm building or buying a web agent for my company, what's the takeaway?
The big lesson is that environmental prompt injection isn't just text in a page. It can be pixels you don't notice. If your agent acts on screenshots, treat the visual channel as untrusted input. Build layered defenses, runtime checks for suspicious rendering behavior, conservative policies for sensitive actions, and tests that include adversarial pages, not just happy path flows.
And if I'm a researcher, where should I push next?
Two directions. First, transferability. Optimize attacks that work across models and varied rendering stacks, and in turn, design defenses that break that transfer. Second, robust evaluation on dynamic real-world sites and authenticated flows, where layout shifts and access controls complicate both attack and defense.
And maybe standardized benchmarks so teams can compare defenses apples to apples. We've seen that help in other domains.
Totally. And sharing code or pipelines would help with reproducibility, both for verifying the attack and for testing mitigations.
Quick recap before we wrap. WebInject shows you can steer screenshot-driven web agents by making tiny, web page-level pixel tweaks. The key move is learning a stand-in for the screenshot pipeline, then using careful optimization to keep changes stealthy but effective. It's practical when an attacker controls the page, and it outperforms more obvious or unrealistic baselines.
And the counterplay is to treat pixels as potentially hostile. Add checks between what the DOM says and what's drawn, slow down risky actions, and investigate ways to make the rendering path less friendly to gradient-based attacks.
Exactly. It's a reminder that the prompt for an AI agent isn't just words. It's the whole environment the model perceives.
That's the show. If you enjoyed this deep dive into WebInject, stick around for more research breakdowns next time on AI Podcast.
Thanks for listening. Take care, everyone.